Cool. Yeah, thanks for the warm introduction. Really happy to be here today. Today, I think I'd like to kind of talk a bit about a lot of what's been on my mind the last few months with regards to where we are in terms of the progress of science and figuring out what's missing for robotics foundation models. I think there's so much energy and excitement in seeing how much progress we've made. And I think a lot of us are still wondering, though, what's next. Today I'll showcase a few different works from a really large team at Google DeepMind. And this is definitely not just me, it's presented on behalf of a really large team. So roughly then at a high level, in today's talk, I'll cover a few different areas. I'll first start with what exactly I mean by robot foundation models. This is very much an overloaded term maybe, and exactly figuring out what that means will be a good start of the talk. I'll then dive into three explicit components that I think are very important for next steps of understanding robot foundation models. And finally, we'll wrap it up with a bit of forward-looking philosophizing. So to really think about what a robot foundation model is or should be, I think it's helpful to take a look at how we got to where we are today. This is the classic sense plan act loop where a lot of robotics progress, even learning-based systems, have seen a lot of progress by using off-the-shelf perception systems, some kind of planning module, and then some kind of low-level actuation. And recently, right, what this looks like in practice is we take a vision language model, that's the perception stack. We take some language model for some kind of planning and reasoning. And then finally, we have some learned low-level control policy. But here, there's two things here which I think kind of give me some hope for where we can go, and something that looks wrong with this picture to me. One is that the modules that we're using off the shelf weren't necessarily optimized with robotics in mind, right? We are taking very performant VLMs and LLMs from NeurIPS and CVPR and what our friends in foundation modeling are doing, and we are finding that we can use them for robotics very well, but they weren't necessarily designed with robotics and decision making in mind. And the second thing is that the way that we're stitching together these modules is oftentimes right now quite engineered in heuristics, right? Which is working quite well in a lot of settings we're thinking about, but I would still argue that the communication bandwidth of these bottlenecks is still quite narrow and will become limiting at the limit. And what I argue then is that because we are now at the point, I would say that we are starting to really feel the pain of these bottlenecks, these limitations, is that the trends we've seen elsewhere in language and vision, we're going to start to see in robotics, right? The foundation modification of robotics, where the barriers between vision and language and control, we're going to start exploring how we can break these down and try to take more of the destiny of robotics, so to speak, into our own hands and actually creating foundation models which are optimized for robotics, which are designed with low-level control in mind. But that's not the only reason I would say, right? When we really take a step back and say, okay, great. Okay, so that's what a robot foundation model might look like. We're going to break down the barriers. Why do we even need to do this in the first place, right? And the first reason that I just alluded to is that, well, it's the clear next step, right? We're going to go from taking off the shelf foundation models that we download and take from our colleagues in other fields, and we're going to try to, maybe create one ourselves, or we're going to make them better with kind of the priors and structures that we've discussed so much, for example, in the conference this week. But the next reason I would say is that actually this is not just nice to do, it's actually necessary to do. If you think about a lot of the robotics progress that we've seen, going from bin picking, picking a lot of objects, doing that very well, going to understanding how robotics mobile manipulation works in one room or one building. But the gap from that academic level research to the chaos of the real world, right? The unstructured in the wild nature of where we now today want to deploy our robots with all of these hyped up startups and humanoids, right? It's like clearly there's a lot of complexity in the situations where we want to deploy our robots with the elderly, with our pets, with our children, and so many novel scenarios. I think the only sign of life, right? The only existence proof we have of a technology that can operate in the complexity and the generality of the real world so far seems to be foundation models, right? I think they're clearly deployed, not perfectly, but they're able to operate at the generality of the in the wild distributions, data distributions, and I hope we can leverage those properties in robotics as well. So we can see then, why have these non-robotics foundation models worked in the wild and these very difficult and unstructured scenarios? And I think there's three main properties that I really think are very important, right? One is, I think, in foundation modeling, folks have understood the scaling laws of how to really get benefits when you add more resources into data, into model size, into compute. Seeing that generalist, learning, generalist models are often beating specialized models. Another thing is, I think these non-robotics foundation models are trained with very large bandwidths. They have high bandwidths. They're trained on very heterogeneous data distributions, and I think then at inference time you can see emergent prompt engineering, few-shot learning, etc. And finally, I think one thing I really like from the foundation modeling community is they've made progress towards more scalable evaluations, predictive benchmarks, and shared kind of evals, which kind of accurately reflect how these foundation models need to perform at deployment time. And in robotics, right, I would argue that we don't necessarily know what these three pieces look like. The topic of the workshop, I guess I was originally in the morning workshop where the theme was learning methods for versatile and reliable manipulation. I would argue map quite well to these three pieces of foundation models that work, right? For scaling laws, when we say learning data-driven systems, I think we'd also like to have some confidence that we know the dynamics of how our learning is going to go. We want versatile manipulation, right? And that it's very robust in all sorts of situations that can generalize. I'd argue that high bandwidth context is what's working in foundation models. And finally, if we want reliability, well, we need evaluations, benchmarks, and to really understand that we're testing and measuring in a very kind of robust manner. And the first hot take, and I'll drop a few today, is that I think today our state-of-the-art 2024 technology is not yet ready to solve general purpose robotics. I think we're if you just kind of snapshot algorithmically where we are today and all you did was apply, maybe money or data, I don't think we're necessarily ready to solve robotics. I think there's still a lot of science and a lot of research and paradigm shifts that we need to unlock. So then let's dive a bit deeper then. The high level areas that I mentioned, I think one of the first one that comes to mind is scaling laws. In foundation modeling, once again, I'll just draw upon what we know kind of works, or at least seems to have a bit more understanding than where we are in robotics. In language modeling, right, starting from GPT-2, from chinchilla optimality, I think there was some work done on the physics and the learning dynamics of how you can scale up these language modeling systems. They found these nice power law distributions of how capabilities and loss could scale as a function of compute, dataset size, model parameters. And I think this is very interesting, right? Because like when the language modeling community convinced themselves and others that they kind of understood the dynamics of like, hey, when we add XYZ, we're going to get performance gains, and this is how what we should expect. You see plots then like the bottom. This is from the GPT-4 paper where they did their experiments and iterations in hyperparameter search at smaller scales, with the confidence that their lessons would still project into the future, right? These are not just retrospective scaling laws, they are predictive scaling laws. And I think in robotics, we would like to be there, right? We would like to have the confidence that the work that we do today, the research and the engineering and the investment, is going to translate into predictable gains in the future. I think maybe we've convinced a lot of venture capitalists that we understand this, but as scientists and researchers, I would not say that we have confidence that this is true right now. I do think, though, this year has been a year of a lot of, sparks of life, signs and signals that, that are vaguely positive. And I'd like to highlight a few ones that have changed my mind over the past 2 years. And the specific question I'd like to ground this in is like, when do we know that scaling will help us? And I think the hardest test you can possibly pass is imagine that you only care about your specific robot in your specific deployment scenario, be that your lab, a task, an environment, a scene, whatever. But if you can pass that test and you can show that scaling helps you in your scenario, I think that's a very good bar to hit. One of the first results I saw this was work from our team from 2 years ago called RT1. We collected a large off-scale, teleoperated expert data set. And then we kind of studied when we trained, large-scale imitation learning, behavior cloning transformers, what would happen, as you kind of ablated model performance as a function of dataset scale and dataset diversity. And I thought was very interesting is we found that both dataset size and data diversity mattered, but you kind of needed both in conjunction. It seemed that a minimum threshold of data diversity was very important. And then in the next work that we kind of followed up with last year with RT2, vision language action models, we started treating robotics data a bit more apples to apples with internet data, like VQA data. And there we found that when we kind of co-train robotics data alongside internet data with a high capacity model backbone, we actually saw some positive transfer of these internet concepts, these internet semantics sort of leaking through into control, which is very great to see, because in our robotics data, we never saw things such as celebrities or country flags or healthy fruits or company logos. And yet we were kind of seeing some of these percolate through, and now our low level control could showcase some understanding of these high level concepts. And finally, and also recent work from earlier this year, the open cross embodiment effort and the RTX line of models, we showed that by training on additional robot data that wasn't your robot could still get you gains in your robot setting. And in this plot here, what it's showing, the rainbow bars show the performance of a single cross embodiment model checkpoint compared against specialist baselines, which were only trained for the robot that they were evaluated on. And this is a clear sign, I think, that on average, our generalist model, by making the problem harder, training on more robots, you even got gains in your specialist setting. And I would say, like, for example, a few years ago with single to multitask learning in the RL literature, this wasn't always the case, right? Like if you cared only about your specialist setting, oftentimes adding multitask auxiliary objectives would decrease performance on your specialist, maybe to give you sample efficiency or generality, but it would decrease specialist performance. And I think whenever we see signs that you can get gains in specialist performance, that's really exciting to me. I think though, at the end of the day, these are still in my mind kind of unpredictable when we see these gains, right? We see that, like, yes, there's signs of life. We're very optimistic. It's very exciting, but we don't really know. We can't really expect the kind of transfer I just showcased to always happen all the time at very high performance. I'll just highlight some dirty laundry here, right? One is that I think vision language action model training is still kind of more of an art than it is a science. It requires good intuitions, good engineering, but at the end of the day, a lot of the positive transfer we see is kind of what we find ad hoc. We haven't planned for that kind of transfer a priori. And I think here's some examples of when that transfer did not happen, right? For example, we find that VLAs can fit VQA distributions and robot distributions, but when you mix the two, it's not obvious when this transfer will happen. Another example is reasoning, right? I think in RT2, we kind of showcased some positive examples of chain of thought reasoning, first asking some kind of task, and then, an intermediate chain of thought here. For example, what do I need to hammer the nails? The chain of thought says rocks, but then we find that sometimes a low level action won't obey the chain of thought. And I think this is very interesting because now that the physical chain of thought reasoning has generalized to our robotics visual distribution, but then kind of the consistency of reasoning to action didn't necessarily transfer right out of the gate. But I think there's a ton more research, right? Especially in the world of vision language action models. I think action representations, how we tokenize, how we weight our data mixtures. These are all big unknown problems that, as I said, are more of an art. They're kind of a black magic, just kind of, some researchers just staring at spreadsheets of data distributions and data sets and just kind of coming up with arbitrary heuristics. No large scale ablations, not a lot of principled fundamental science. The screenshot here is one of the works I've seen from a few months ago that I really like, from Alex Toshev's group at Apple, where they're looking at different tokenization choices, where in, for example, in RT2, we kind of just chose the most naive parameterizations. And, another major aspect, in addition to how you train VLAs, the architectural design decisions, I think understanding the scaling trends for robotics is also important. I think, one might ask that, okay, great, you just mentioned, Ted, chinchilla optimality, you mentioned language model scaling laws. Did the exact same laws just apply, copy and paste to robotics? And I would argue probably not, right? I think in robotics, it's easy to convince yourself that not all data is created equal, right? You can have a billion hours of just free form robot motion, just waving your arm around, and that's probably not very useful data, right? Even though it's a lot of tokens. And so I'd argue the axes of what it means for robot data to scale might be very different from what we expect from language, where you expect everything is just the same, right? So I think what this means, here's two interesting papers I like recently that are showcasing this direction, but I think they're just an initial kind of data points on this research field. But I think the hot take here is that because we don't yet know what the scaling laws of robotics looks like, if you look historically, a lot of medium scale data collection in the past has not survived past one paper, right? We collect a lot of data, it gets us really great results. Then you look 2 years down the line, the data has almost zero marginal utility. And I just, we would just hate to be in a point today where we've harnessed a lot of excitement, a lot of resources, a lot of investment. We collect big, large scale data, in product deployments in the world. And then 5 years down the line, we found out a lot of it was not needed or not useful at all. That would not be great. So moving on then past scaling laws, high bandwidth context. This is what I mentioned earlier on, which I think in language models, we've seen a lot of great success where they operate under very unconstrained interfaces. But when you look into robotics with how a lot of popular language conditioned policy learning works operate, it's at an episodic structured template language, right? Like pick A, place in B, right? Move A near B, almost like a fancy one hot. We're not really leveraging language for the reason that language is good in language models. And maybe the reasoning is that we've been starting by, from these like very fancy language model demonstrations where high level semantic knowledge is very robust, and we're kind of trying to just pattern match and fit what works in language models into robotics. But maybe by doing that, at least the ways we do that today with very high level abstract language, we're giving up so much. We're giving up what makes robotics interesting and hard. We're giving up the low level, rich contact, the physics, all the knowledge we know that is important from the motion planning in classical control literature. It's sometimes hard to, maybe if you just squint at this, hard to understand how you might even begin to express a lot of these very nuanced concepts in language. And so today I'd like to highlight kind of two works that recent works that tried to present one possibility towards that. One is, called RT affordance, where we kind of started by looking at vision language action training distributions, right? This is what I just mentioned with co-training the robotics data, the green bottom left data alongside blue internet data with maybe some more spatially grounded vision data on the upper right. If you really think about, if you like zoomed out and like thought about like the data manifold, right, of like where these data distributions lie relative to each other, I think they're actually quite different, right? And like what we need is to bridge these very different distributions with some kind of shared, intermediate representation. And what we propose in this work is to use affordances as that. Affordances, what we mean by that is thinking about what makes robotics hard, the contact, the grasping, the rotations, and really expressing that as, kind of as poses, as some kind of representation, which can convey this information, which might otherwise be leaked through if you just rely on high level language. So towards this, affordances, they're expressive, I think, because they fully represent what's hard about robotics. They're lightweight, and they maybe kind of offload the cognitive burden from the high-level policy from having to learn all of this affordance-based reasoning just via low-level control. It just provides like an intermediate kind of planning hierarchy where it can try to learn these concepts. Looking at the method broadly, it's a quite a simple adjustment from our standard vision language action model training. We basically just break up a hierarchy into a high level planning and then low level planning. For the high level planning, we're taking in the current image and the original text instruction, and then we're predicting an intermediate affordance plan expressed as text, which we can then overlay into the current image as a goal image. And then for the low level policy, now it's conditioned on this, visualized affordance goal image alongside the text instruction to produce the original low level control outputs. And the idea here then is that now that we have this kind of hierarchy of reasoning over affordances, we can get great generalization at test time to out of distribution shifts, as well as on in distribution behaviors. This was originally motivated by the fact that a lot of our prior works on exploring different representations and different languages was that like there were certain categories of objects where we noticed we were consistently seeing generalization failures. These are objects that have to be approached or grasped in a specific way, such as objects with handles or which are asymmetric or which have very unique affordances. And this model, is clearly a way to kind of showcase why that was a blind spot before, and by filling in that blind spot, we get much more robustness on these scenarios. And that was kind of one way then to look at an end-to-end training method by introducing hierarchy to improve end-to-end control, both on the reasoning over affordances, but also low-level control. Stepping back a bit, though, in general, I think it's interesting to think about how you might connect the broader problem of connecting foundation models, which are used to internet data, and now you have to bridge them to low-level control, which is, again, as I mentioned, maybe this super different thing from what you expect from the web scale pre-training data. One way is end-to-end, right? Better vision language action models, skill discovery, something like that, where you're optimizing both the high-level reasoning as well as the low-level control. Another way is maybe you can just abstract away robotics as black box. It's just tool use, right? You assume that the low-level policy can handle the difficult bits of interacting with the world. You assume it's a frozen policy, and then you can just do better foundation modeling, better reasoning in order to orchestrate that low-level policy. You can see this with works like that we did in the past, such as SEICAN, a recent work that I really like, embodied chain of thought, inner monologue, etc. But in contrast, I feel like one area that we haven't really studied as much is what if you freeze the reasoning, right? What if you view the foundation modeling high-level reasoning as the black box, and then you actually improve and optimize your low-level control policy in order to be more flexibly controlled by some reasoning system? And to do this, right, maybe one natural interface is maybe it is still language, right? So I think even though I was mentioning language has all these limitations, maybe this is the most natural way if you freeze the foundation model that you can expect it to control your policy. And if you do this language-based reasoning, maybe the issue wasn't language itself, but the way we were using language. I think a lot of the ways that I showcased the limitations of was more on the right of the spectrum. If you think about this roughly, this is like left is more granular and right is more coarse. So right is like episode level templated language instructions, pick A, place near B, move apple near Coke can. Very coarse, very high level. We can move it slightly left by rephrasing with hindsight labeling, right? And other works such as I see like Nils from Moritz and Rudy, or works such as a language table from our team at GDM of like a hindsight relabeling. Or you can go all the way to the left with like very granular, like one second horizon language motions of describing how the gripper should move itself. But I would argue that both ends of the spectrum are not very friendly for foundation models. Foundation models maybe don't understand these task level, episode level instructions. They also don't yet understand maybe the groundedness of having to reason about like 1 second horizon motion centric strings. So maybe what we want is something in between. And our recent work Steer, which I just presented briefly as a spotlight 30 minutes ago, but I'll just like maybe so I won't go too deep here, is thinking about how we can really design a method that can be steered in that nice Goldilocks zone in the middle between being too coarse and too granular. What we did here was dense language labeling. And the way we did that was by focusing on like, what does it mean for a low-level control policy to be steerable, to be controllable in a way that like a VLM can compose it at test time. What we did at a high level is we focused on the grasps, on what matters, the contact, the rotations, the orientations, how you actually interact with objects as maybe the correct semantic abstraction level. That's where it's low level enough closer to actions, but also high level enough where it can be semantically understood by a VLM, where if a VLM has to operate over this kind of state space, maybe it's the correct level of hierarchy. What we see then is that training then is on the left here. We've kind of learned these more granular skills with dense language labeling. And then on the right here is how you might use this at test time. You see a new, everyday object on an unseen task. Then the foundation model can natively already kind of reason using the skills that we learned densely to deploy at test time. I'll zoom over this a little bit, but we see better steerability compared to pre-trained models such as OpenVLA and RT1. We can see this quantitatively by seeing how steer can adapt to new situations, generalize new objects, which need to be interacted with in very unique ways. As kind of visualize what this rollout means is that steers on top. How this is working is that the VLM is controlling the low level policy and basically choosing which kind of grasp approaches to use. In theory, right, a vision language action model has seen potted plants. It's seen these kinds of motions. So in theory, it should be able to do this implicitly, but you see that isn't always the case. It overfits the training data distribution of the low level actions quite often. an RT1, right? It's never even seen any of the semantic data. It has no chance of interacting with objects in, you know, predetermined behavior modes. And our original motivation is, you know, seeing whether or not VLMs can control it completely autonomously. In the sake of time now, I'll just maybe skip scalable evals. I think it's very important. I'm sad I have to skip it, but I think it's also the part that I think we know the least about. I think the main point here is that I think you know, world models can help us, but real world evals are always going to be the most important thing. But this is kind of going to become the bottleneck as we train more and more generalist policies. I'll just end on this slide here, which is, you know, just being a very intellectually honest grading of where we are today. The three topics I think are missing pieces, right? Scaling laws, more steerable robot policies, and scalable eval. I think, you know, there's been a lot of excitement, a lot of hype, but I don't think we're very close to solving the science behind it. I think there's a lot of work that we still need to do as a community, you know, this year, next year, and beyond. And with that, I'll just end it here and open for questions.